So suppose we're asked to find the distance from a given point to a geometric object like a plane. All right, so so when we say the distance from a point to a plane, we mean like the minimum distance, right? So what's the distance to the closest point on the plane to it? So let's see. So the picture that goes with this is something that looks like this, right? So we've got here. There's the point of interest is right here, 1, 0, minus 2, and then these spherical shells represent level curves of the distance function to this particular point, right? So all the points at distance 1 from the one we're interested in are going to form this sphere right here, and then there's more, larger and larger spheres as you go further and further away. So then the plane that we're interested in is this blue one over here. And if you look, you can see that the intersection of the plane with these spheres is, as you can know from your visual imagination, are these circles. There are these concentric circles right here. And so somewhere there's going to be the sphere to which this plane is tangent. And it'll be they'll just have a single point of contact right there. And so that's the one that we're looking for. That's the one that'll tell us what the distance is. So for this problem, the objective function is going to be the distance from a given point to this fixed point that we're interested in. And so that's the square root of, and then we've got x minus, the difference in the x's, and the difference in the y's, and the difference in the z's, all squared, and then added up. So we're just using good old Pythagoras, right? So this function here is the distance to p naught function. Okay, and our constraint equation is going to be we want x plus 2y plus z to equal 4. Okay. So the very first thing that I notice when I look at this problem is that our objective function is ugly, right? It's got this big square root, and nobody likes to have to mess with the square root, differentiate it, so on and so forth. It's going to cause chain rule, whatever. So first rule is we're going to ditch the square root. And this totally looks like cheating, but it actually is completely legit. So here's the reason why. The square root is an order-preserving function. Okay, so now order-preserving, this means that it's monotone increasing. So, for example, whenever you have a function that has a positive derivative everywhere, then when you look at how the function behaves, so we're just working in single variables here. So square root function looks like this. What I'm saying is that if we have a less than b, and then we apply f of a, and we apply to get f of b, then if a is less than b, f of a will still be less than f of b. Right, so the ordering between these output points corresponds to the ordering between the input points. That's what I mean. And so other examples of functions that this is true for are like e to the x and the logarithm function, right? Both of these are increasing everywhere that they're defined, and whatever else. So we can go with the new and improved objective function, and I'll call it f And it's just the same thing that we had before, but without the square root. And again, just in case you think this is somehow some slick cheat, let me show you another picture. So down here we've got some like crazy complicated makey-uppy function that I just put together on Mathematica, and I had it plot the function. I had it plot the function f up top, and then I had it plot the square root of f underneath. And so you can see that even though the function values are different, the maxes and mins occur in the same places. That's the key point. So if f has a max here, if the square rooted function has a max here, then the actual function will have a max in the same, at the same location. The value of it will be different, right? Because typically the value of f and the value of the square root of f are going to be just different, or I guess maybe I should say x and square root x are typically different numbers, yeah. But those maxes and those mins, let's see, I guess there's like maybe a min, maybe even this whole region right here is a min, and this whole region right here is a min, but they occur directly above one another. In other words, they correspond to the same points in the domain. So what we can do is we can just say, hey, this guy is ugly to deal with, so forget you. I'm just going to work with f instead, and I will locate the minimizers and the maximizers of this function instead of the original function. And then all I have to do is remember to take the square root at the end if I actually need to find the value, the maximizing or the minimizing value. Okay, so given that, let's proceed with the program. So the standard thing to do is step one, we solve the constraint for a variable. And this time, let's see, I think I like to pick on z for whatever reason, so I solved it for z again. So it becomes 4 minus x minus 2y, right? So I'm just looking at this guy right here and solving it now for z. And then we can substitute. And there's nothing special about z. You can solve it for x or y or whatever you like. I don't know, I like to pick on z. Substitute this into the objective function. And so now we see f of x, y, z becoming f of x, y, and then we build the constraint into the function. And so I'll call this new one just f of xy, little f of xy. And so when we do that substitution, what do we get? We have x minus 1 squared plus y squared plus 6 minus x minus 2y squared. Okay. So now it's time for good old first derivative test. So we compute the gradient of our constrained objective function, and this will give us, let's see, so mucking around on some scratch paper, we've got 4x plus 4y minus 14 and 4x plus 10y minus 24. And so we set this equal to 0. And we get a couple of equations. We get 2x plus 2y equals 7 from the first one, and we get 2x plus 5y equals 12 from the second one. And so let's see, so if I subtract the first equation from the second equation, then I'm left with 3y equals 5. Right, so I just subtract, and these ones cancel, and this gives me a 3y, and then this one gives me a 5. And let's see, so now I can solve for y to get 5/3 and x to get 11/6. So the only critical point, and from the geometry of this, it should be clear in advance that there's only going to be one critical point, and that's just because there's only one point on a plane that's of minimal distance to another given point. And so the critical point is, what did we say, 11/6, 5/3. And we were asked not to find the closest point on the plane, but actually to find the minimal distance there. So let's see. So then we use our constraint equation. And so we plug in, so what was this? This was 4 minus x minus 2y. So this is 4 minus 11/6 minus 2 times 5/3, and we get minus 7/6. So that point that's on the plane closest to P naught is this one. And like I said, we don't actually need that for this problem. I'm just writing it down because for some of the problems in the homework, you will need it. Let's see. And if we wanted to do second derivative test, we could, but we know in advance that it's going to be a minimum. There's no boundary to check. The only thing that remains is the actual distance. So the minimal distance is going to be the distance to this point. So we're going to be looking at 11/6, 5/3 minus 7/6, and subtracting off P naught. And when we do that, let's see, so the difference in x coordinates is going to be 5/6, and the distance in y coordinates is going to be 5/3, and the difference in z coordinates is going to be 5/6. So we're going to square those, add them up, and take the square root by good old Pythagoras, the dead Greek, and that gives us 5/√6. And that is the square root of our constrained objective function evaluated at 11/6, 5/3. So there is our answer.